I'm Eileen, and today I will walk you through the architecture of our MSCI 495 assistant with semantic caching. So I use Figma tool to draw this diagram, which is pretty convenient for both drafting and presenting. So for the first part, let's start by looking at the entire flow from our user input to response generation. So a user interact with our assistant through a chatbot or app service by submitting a query. So the query is sent to the API gateway, which is here. The API gateway serves as the entry point for our all backend services. The gateway handles like a routing or security check. So after arriving at the API gateway, to optimize the overall performance, the system first adopts semantic caching. Using the semantic caching is check if a similar query has been processed recently. So if the cache contains a relevant response, it is returned immediately to our user. So in this way, it avoids the need for further processing. So this semantic cache is stored in Cosmos DB. Cosmos DB, which is a MongoDB core API, offers a distributed storage and global low latency queries backend solution for high concurrency and real-time caching needs. So if our semantic cache do not contain a response, like a recent response, the query is forwarded in another way to our Azure AI cognitive search service. So this component handles semantic retrieval, where it compares and ranks the top K relevant documents based on the cosine similarity between the query and the pre-indexed document. So Azure AI cognitive search service is a great tool to offer semantic search and index optimization, enable efficient large-scale data retrieval and ranking. So after that, the retrieved documents are sent back to our API gateway and then directly to our Azure OpenAI service on large language model deployment. So for example, we deployed GPT-4o as our model. So the model we deploy is highly dependent on the region availability, such as the West US or East US. So using different region to deploy may lead to network latency. So GPT-4o used the retrieve document from the cognitive AI search and it generates a contextual response, which is sent back to our users through the API gateway. So outside the whole process, another component is called application insight. It monitors some key system metrics and offers a real-time performance analysis and log query capabilities. So in this way, it helps to monitor our system performance and quickly diagnose issues, and which ensure the systems remain reliable and scalable. So for the second part, we are talking about the online processing and offline processing. So online processing is happening in real time to handle user queries. So main steps include user send queries to Azure Cognitive Search Service and retrieve from it, and response generation using our large language model, which is central to the RAG, which is also called a retrieval augmented generation pattern. So it generates the response by combining user queries and with the retrieved data content, document content, But so in the end, it improved the quality of our generated response. For offline processing, it is responsible for document preparation and indexing. External data sources such as policy documents are uploaded through the document intelligence. So document intelligence can process and extract key information from uploaded documents and generate a semantic embedding and store the indexed data in Azure Cognitive Search, which is this way. So this process ensures that the document can be quickly retrieved during the online queries. So to summarize, this architecture integrates semantic caching, online reg processing, offline indexing to optimize the both performance and scalability. So key AI service we introduce like cognitive search, OpenAI model deployment or Cosmos DB and application insight. They are working together to deliver a fast and context-aware assistant experience. Thank you.